Yeah. Hi, everyone. My apologies for the technical issue that I figured out. I would like to thank the organizer for giving me the opportunity to give this talk, present my work that has been done with many collaborators, and thanks also to them. So I will start this presentation by defining what is an LBV. And as their name suggests, an LBV is blue, very hot, very luminous, but also extremely variable. And they go through as there is a cycle variability, so it's a kind of irregular photometric and spectroscopic variability on a time scale of about 10 years. And if you look here at the light curve of AG-CAR over the last 40 years, you will see that AG-CAR has a V magnitude that oscillates between 9 magnitude in the V band and 5 magnitude in the V band. So it's extremely variable. And you can also see this variability in the spectra. Sometimes the star look like a blue supergiant, O-star, Wolf-Rayet star-like spectra. And other moment, the spectra looks like more like a early A or even F type stars. And so to be classified as LBV, the star should meet all these different properties. And you also have another subgroup of LBV, which are the dormant ones, that share common characteristics with the confirmed LBV, but without the SDR cycle. And as you know, most of LBVs are surrounded by a circumstellar nebula, as it's shown here in this picture. So an LBV is thought to be a transitory phase between O stars and Wolf-Rayet stars in the single star channel scenario. But that scenario suffers also from several problems. First one is the measured massless rate during the outburst of S Doradus star in the SMC, which appeared to be too low to match with this picture of transitory phase. Also, the progenitors of some type 2 supernovae have LBV-like mass loss rate, while in single star channel, the LBV do not explode as type 2 supernovae. And most recently, there's a lively debate in the literature about their relative isolation. And for instance, the author of this paper, Smith and Tumblestone, in 2015, study the projected separation to the nearest O-type stars, the nearest O-type stars, and they show that the LBVs are actually quite isolated if you compare their population, for instance, to the O-star population or to the Wolf-Rayet population. And so this relative isolation means that the LBV should live longer than classical O stars or classical Wolf-Rayet stars, and so they might be they might be coming from a binary merger or even through mass transfer involving Rochelov overflow. Rochelov overflow. And so if you look at the multiplicity of LBV across about multiplicity of massive stars across the Hirschsprung-Rosset diagram, we see that O stars are mainly found in binary system. Actually, over 70% of them are found in binary system. For B stars, is closer to 50%. For classical Wolf-Rayet stars, we are above 55% for the W and E, so the early nitrogen-rich Wolf-Rayet stars, and above 70% of the carbon-rich Wolf-Rayet stars. But if you look at the red supergiant phase, this binary fraction significantly drops to 15%. So what is the situation in the LBV phase? And so far, only 4 LBVs, either confirmed or dormant, were found to be binaries. There are several attempts to characterize their multiplicity. For instance, the work of Christophe Martaillan in 2016, working on HST imaging and of 7 galactic LBVs. So they claim that 22% of them were found in binaries. And the work of Yael about this, her X-ray archivized survey, where she claimed that the binary fraction is between 26 and 69%. So our project right now was to focus on optical spectroscopy, new and archival, and we focus on stars with Vmag lower than 13.5 magnitude. And we focus also on data taken during the same Esderada cycles. So we are not affected by this huge and crazy variability of the star. We also combine that sample with an H-band interferometric snapshot. And so for that, we target stars with H-band lower than 6.5 and a V-band lower than 13.5. So we have a sample constituted of 19 stars, including Eta Carinae in spectroscopy, and 18 stars, including Eta Carinae, HR Carinae, and pistol stars. So if we look at those two data sets, we have 11 objects in common. So about the spectroscopy, actually the detection of LBV companion is quite difficult because of the large luminosity of the LBVs and their strong variable stellar winds. So what we did is to use cross-coloration techniques, mainly focusing on metallic spectral lines so that we are not as affected by the wind as we can be, for instance, with hydrogen or helium lines. And we use those two criteria that have been already used in several papers. And what we did is to let these parameters, so delta RV min, vary between 0 and 100 km per second. And what we see is that the observed binary fraction drops significantly until 36 km per second, and then is more or less stable. So this kink here represents where we put our threshold. And so everything below that threshold is characterized by intrinsic variability of the stars, either through their winds or their pulsation, whatever. And everything above that threshold is due to binarity. And so we claim that the observed binary fraction is around 26% in our data. But of course, we need to correct that number by the observational biases. And so in spectroscopy, we are sensitive to the number of spectra that we have, the observational time base that our spectra cover, of course, the low inclination of the system, the low mass ratio, the high eccentricity, the long period, and so on. And so we model all these observational biases. We came with different models and we correct what we observed, so the 26%, with those correction, and we obtain a binary fraction of 62% in spectroscopy. Now, if we look at interferometry, we use Candid, which is a tool specially designed to find faint companion around stars. So it's based on a disk to mimic the primary star and point to a source to mimic the secondary star. We do that basically because in spectroscopy, we are sensitive to angular separation between 0.1 and 1 milliarc second. But in interferometry, we can probe larger separation, sorry, between 1 and 100 milliarc seconds. So we can probe a wider orbit. And we find basically companions for 14 out of our 18 stars. But of course, we wanted to also test different configuration. And because the LBVs are quite affected by their strong wind, we also test configuration reminiscent of single star. And so we use a point source to mimic the star, but a Gaussian profile to mimic their wind. And by doing so, we found that 3 objects in our sample have similar chi-square if you use LitPro or if we use Candid. So we cannot disentangle exactly whether or not those stars are binaries. But for 11 other objects, we have a better chi-square with Candid, so with the binary model. And so we can pretend that the binary fraction among the interferometric data are between 61 and 78%. So it's quite high. So far, these are interferometric snapshots. So we only have one observation for each star. And so the main issue so far, it's we still would like to characterize things, to characterize the orbital properties of the star. So we need to collect more and more observation to actually follow the star, the companion. And so far, all those numbers, so between 61 and 78%, are based on statistical argument, because we cannot be 100% sure that the companion that we found are physically associated with the LBVs. So more and more data will come in the future, maybe after the COVID episode at ESO. So we hope to get data soon to continue that monitoring. So to conclude, and what can we learn? Of course, the binary fraction among LBVs is very high, basically like O-type stars. But with the interferometric data, we were also able to probe for the first time the radius of those LBVs, and we have direct measurement of their size. And we are basically between 50 and 500 solar radius for the radii of those objects. So it's not possible to have short period system. We only have wide orbit. So since also the binary fraction is so high, we can also reject the fact that LBVs are formed through mass gainer episode. Now we need to wonder how to go from high fraction of O stars in short period binaries to high fraction of LBV stars in long period binaries. And for that, there are two possibilities. First, the LBVs can only come in a long period system if you consider the single star evolution scenario. Or if you look to the binary evolution, they can be formed through binary mergers in a triple hierarchical system, or even by either binary system, or through a fully non-conservative mass transfer. And if you want to know more about that, the paper has been recently accepted, it's now on press, and it's available on arXiv. And thank you very much.
Thank you, Laurent. So, do we have any questions? Okay, I see a question by Noam.
Yes, very interesting. I have a question about your summary, actually. Can you explain the last 3 points? What is a reject and kicked mass gainer hypothesis? What is it? What do you mean by long and short period? Can you give time scale?
Yeah, so the first point, the kicked mass gainer, is actually when two stars are interacting, you have a transfer of mass and angular momentum from the donor star to the gainer star. And so at one point, the donor star will explode as a supernovae and kick the mass gainer.
Oh, okay. Okay.
So that was a scenario proposed by Smith and Templeton. But yeah, basically we don't find any evidence to prove that scenario.
Okay.
And about the time
long
scales,
period, yes. What is you mean by either single star evolution in long period?
Yeah, so long period means that we have a period more than a few hundred to few thousand days. So the two stars will evolve basically without any interaction with their components.
In Eta Carina, the orbital period is 5.5 years, so it's 2,000 days or something.
Yeah, so it's basically that regime I want to talk about.
Okay, so it's not really single star evolution. Even at 3,000 days, they will still interact.
Well, it depends. If the star evolve basically without any contribution from the outside, not like Eta Carinae, because there you have a triple system at the beginning.
No, come on. In Eta Carinae, we see two stars. Triple is a model. We see now binary. So in Eta Carinae, the binary orbital period is 2,024 days, and we see strong interaction even. So this requires what is a long period that you refer to as single star evolution.
Yeah, but it also depends on the characterization of their orbit.
Yeah, of course.
For Eta Carinae, I mean, it's very eccentric. So at the periastrons, you can still expect to have some influence of the companion.
Yeah, but I expect most LBV to have high eccentricity. Okay.
Yeah, so that's why,
yeah.
I mean, that's the purpose of this work. It's in a few years when we have the chance to get more data, we will be able to produce the orbital parameter distribution of those stars, and we will know a little more about how.
Okay, this is very good. Last question, P Cygni. Did you have P Cygni on your sample?
Yes.
And then what did you find?
We find that it's possible, it's a possible binary.
Amit Kashi, who is here, predicted 11 years ago that P Cygni has a companion in a 7 years orbital period, more or less. Well, so it would be nice to check it.
To be honest, we are in contact with Noah Richardson. I don't know if you know him.
Yes.
But he obtained 11 years ago an interferometric data point of P Cygni. So now the instrumentation evolved, and so it's more sensitive. So we combine his data point with ours, and it appeared that actually the period is quite long. Of course, with 2 points, we cannot constrain exactly the orbital motion, but the orbit appears to be eccentric if it's a real binary. That's what I can say.
And what is long? It's
I mean, yeah, no, it's not enough. I mean, 2 points is not enough to say something.
Okay, good, very good. Good luck in the future.
Thank you very much.
Very interesting.
Okay, so Laurent, can you stop sharing?